Hello friends, welcome back to my YouTube channel. This is 12th part of my discussion on gas absorption. And in today's discussion, I will be discussing a numerical example. I'm calling this as numerical example number 4 because that would be the fourth example on this topic. And in this example, you will learn how to apply Kremser equation for finding the number of stages in a tray column, for finding number of stages in a multi-stage counter current absorption operation. So let us begin the discussion. To begin with, we will look at the numerical statement. So light oil, which is benzene. So benzene vapors contained in cool gas are to be removed by scrubbing the cool gas with a wash oil in a counter current absorption operation. The operation is to be carried out in a tray column. The gas enters the operation at a rate of 0.250 meter cube per second at 26 degrees Celsius and 1.07 into 10 to the power 5 Newton per meter square, and contains 2% by volume of light oil vapors. The entering wash oil contains 0.005 mole fraction of light oil and has an average molecular weight of 260. Calculate the wash oil rate if it is equal to 1.5 times the minimum rate. 95% removal of the solute is required in the operation. Also find the number of ideal stages required using Kremser equation. The equilibrium relationship is given to us. It is capital Y is equal to 0.125 capital X, where X and Y are mole ratios in liquid and gas phase respectively. So I have taken the numerical example which I have solved it earlier in my discussions on gas absorption, but here I have changed it so that we can learn how to find the number of stages by using Kremser equation. So you have a cool gas that is containing benzene vapors in it. Benzene is being called light oil in this case, and the objective is to remove benzene vapors by scrubbing the coal gas with a wash oil. So the operation used is counter current absorption operation, and the solvent used is a wash oil. The operation, it is to be carried out in a tray column. The gas enters the operation. The entering rate, inlet flow rate of the gas mixture is given to us, but it is volumetric flow rate 0.250 meter cube per second. Temperature is given, it is 26 degrees Celsius. Pressure is given, it is 1.07 into 10 to the power 5 Newton per meter square. And the inlet composition of the inlet gas, that is composition of solute in the inlet gas mixture, it is given to us. It is 2% by volume. The composition is given in percentage volume. The entering wash oil composition is also given to us. It is containing 0.005 mole fraction of light oil. So wash oil, it is a recovered solvent in this case. That's why it is containing some solute in it, little amount of solute in it. The average molecular weight of the wash oil, it is given to us 260, and we are supposed to find the wash oil rate if it is equal to 1.5 times the minimum rate. So wash oil entering liquid rate, we are supposed to find out if it is to be 1.5 times the minimum rate. So entering liquid rate is 1.5 times of the minimum liquid rate. That means in this case, first of all, we will have to find out the minimum liquid rate. The 95% removal of the solute is required. So in this operation, 95% of benzene vapors that enter with the entering gas mixture, they are to be removed in the operation. Then we are also supposed to find out ideal stages, number of ideal stages by using Kremser equation. And now the equilibrium relationship is given to us. It is capital Y is equal to 0.125 capital X, So you can easily understand this is a linear relationship. That is, the equilibrium curve is a straight line. Here capital X is mole ratio in the liquid phase, capital Y is the mole ratio in the gas phase. So this is the problem statement. Now let us solve this. Let us continue. Okay, so first of all, we will note down the given data. So in this case, the operation is benzene vapors. We will denote those by capital E. They are to be removed from their mixture with coal gas. So coal gas in this case is the insoluble gas. So as per our notation, flow rate of this will be GS. The molar flow rate of insoluble gas, which is cool gas, in this particular case is GS. So how this is to be done? It is to be done by absorbing the benzene vapors into a wash oil. So the solvent used is wash oil. So if you have to show the operation schematically, the gas is entering at the bottom. It is contacted with the wash oil, and then after absorbing benzene vapors, the resulting solution, it will come out at the bottom, whereas the gas from which light oil vapors have been removed, it will come out at the top. So you know this notations. I have discussed them in detail in my previous video lectures. So G and L, this represents molar flow rates, and small y and small x, these are mole fractions. So for the inlet gas mixture is coal gas, which is the insoluble gas in this case. Its molar flow rate is GS. So inlet gas mixture is coal gas plus benzene vapors. We are identifying them by E. Then the volumetric flow rate is given to us. Let us denote it as Vn plus 1. It is 0.250 meter cube per second. So we need to convert it to Gn plus 1, where because we need it in kilomole per second. So we will do that. Then the inlet gas mixture is containing 2% A by volume. We need to convert it to mole fractions. Temperature is given to us. It is 26 degrees Celsius, which is 273.15 plus 26. That is 299.15 Kelvin. Pressure is given to us. Pressure is 1.07 into 10 to the power 5 Newton per meter square. Apart from this, for the inlet liquid is wash oil. So wash oil in this case is the non-volatile liquid solvent, whereas solute in it is benzene, that is E. The mole fraction of E in the inlet liquid, that is X0, X0 it is given to us, X0 is 0.005. Then the average molecular weight for wash oil, it is given to us. Let us denote it as MW average, it is 260. Then the required rate, that is L0, it has to be, or LS, it has to be 1.5 times of LS minimum. That is the requirement. So first we need to find out LS minimum, and then after that, using this relation, we can calculate LS. Then in this operation, requirement is we need to remove 95% of E. 95% removal of E is required in this case. So whatever E enters in the gas mixture at the bottom with this stream, 95% of it has to be removed. So when the gas comes out, it will be containing just 5% of light oil vapors in it, because 95% would have been absorbed into the liquid solvent. So requirement is 95% removal of E from the gas mixture. The equilibrium relationship is directly given to us. It is capital Y is equal to 0.125 capital X. Capital Y and capital X, these are mole ratios in gas and liquid phase respectively. And what are we supposed to find? First, we are supposed to find out the required inlet rate. That is, we have to find out LS, and then after that L0. And then we also have to find the number of ideal stages. But this time we are going to do that by using Kremser equation. So this is the given information. We have to use it to first get LS and then L0, and then we have to find the number of ideal stages by using Kremser equation. So let us move ahead. Now let us first understand the approach. Let me tell you the approach. First we will be finding capital Yn plus 1, capital Y1 and X0, because we don't have their values directly. We have to get them. So Yn plus 1, first this is mole fraction in the inlet gas mixture. So first we will be finding Yn plus 1, small Yn plus 1 from the given inlet composition. For that we need to convert percentage volume to mole fraction. Then capital Yn plus 1 we are going to get from small Yn plus 1. Then once you get capital Yn plus 1, you can get capital Y1 from capital Yn plus 1, and for that we can use this information. 95% removal is required. So this information can be used to get Y1, capital Y1 from capital Yn plus 1. Then after that we have to get X0. X0 you can get from small x0, which is given to us. Then we have to find out Gn plus 1 and Gs, because these are molar flow rates. So Gn plus 1 we are going to get from Vn plus 1, which is given to us, the volumetric flow rate, meter cube per second. And how are you going to do that? For that we will use ideal gas law. Then Gs we will find from Gn plus 1 and small yn plus 1. Then after that we will find out Xn max. And how are we going to do that? We will get Xn max from equations of operating line and equilibrium curve. So by using the equations of operating line and equilibrium curve, you can get Xn max. Then we will find LS minimum. That we will be getting from the equation of the above operating line, the operating line corresponding to minimum liquid to gas ratio. Then after that we will get LS and L0. LS we will get from LS minimum, because LS is 1.5 times of LS minimum, so that will give us LS. And once LS is known to us, LS and X0 they can be used to find out L0. Then we have to find out absorption factor, because we need it in the Kremser equation. Absorption factor, we have, it is the ratio of slope of the operating line to the equilibrium curve. And then finally we will find the number of ideal stages by using the Kremser equation. So this is the approach that we will be using for solving this numerical example. Let us move ahead. Okay, now let us solve the numerical. First, let us find out capital Yn plus 1. So percentage volume of E in the inlet gas mixture, it is given to us, it is 2. We will assume the gas mixture to be ideal. So for ideal gas mixture, percentage volume is equal to percentage mole, and that is 2. And then percentage mole can be converted to mole fraction by dividing it with 100. So small Yn plus 1 is 2 upon 100, that is 0.02. And then capital Yn plus 1, you can get it in this way. So capital Yn plus 1 is small Yn plus 1 divided by 1 minus small Yn plus 1. So capital Yn plus 1 is equal to 0.02 divided by 1 minus 0.02. That gives us capital Yn plus 1 as 0.02041. So in this way we get capital Yn plus 1. Capital Yn plus 1 is what we got is 0.02041. And the meaning of this is moles of E per mole of coal gas. And the task is 95% of moles of E have to be absorbed. So this information will give us capital Y1. So let us find capital Y1. So as per the requirement, 95% of the entering gas entering E is to be removed. 95% of this E is to be removed. So therefore capital Y1 will be simply Y1, that is E in the outgoing gas will be just 5% of the entering gas, because 95% it will be absorbed. So therefore, capital Y1 is equal to 0.05 capital Yn plus 1. Capital Yn plus 1 we have obtained. So capital Y1 is equal to 0.05 into 0.02041. That gives us capital Y1 as 0.00102. Then we have to get capital X0. We can get that from small x0, which is known to us. So capital X0 is small x0 upon 1 minus x0. Small x0 is 0.005. So therefore capital X0 is 0.005 divided by 1 minus 0.005. That gives us x0 as 0.00503. So in this way, we get capital Yn plus 1, we get capital Y1, and we have also got capital X0. Let us move ahead. Next, we have to get Gn plus 1, the molar flow rate of inlet gas mixture. And we have assumed ideal gas behavior, and you can apply the ideal gas law. PVn plus 1 is equal to Nn plus 1 into R into T. Vn plus 1 is meter cube per second. So if you use as it is, N plus 1 will be moles per unit time. That is the molar flow rate. So in this case, Nn plus 1 is nothing but Gn plus 1. So Vn plus 1 is given to us, it is 0.250 meter cube per second. T is given to us, it is 1.07 into 10 to the power 5 Newton per meter square. R, we are going to use this value 8314. For that, volume has to be in meter cube, pressure has to be in Pascal, that is Newton per meter square. Amount of substance will be in kilomole, and temperature will be in Kelvin. So temperature is 299.15 Kelvin. So in this case, as I said earlier, Nn plus 1 is nothing but Gn plus 1. So therefore, 1.07 into 10 to the power 5, let us use the values. So 1.07 into 10 to the power 5 into 0.250, that is equal to Gn plus 1 into 8314 into 299.15. That is 1.07 into 10 to the power 5 into 0.250 divided by 8314 into 299.15. So I have brought these two terms on this side. So that will give us Gn plus 1. So therefore Gn plus 1 comes out to be 0.01076 kilomole per second. Now let us find Gs. Gs is Gn plus 1 into 1 minus small yn plus 1. Small yn plus 1 is 0.02 we have obtained earlier. Gn plus 1 we have just got. So therefore Gs will be equal to 0.01076 into 1 minus 0.02. That is Gs comes out to be 0.01054 kilomole per second. So in this way, we have got Gn plus 1 in kilomole per second, and now we have got Gs, which is again in kilomole per second. Let us move ahead. Now let us get Xn max. So for that, we know equation of the operating line is given like this. Ls upon Gs is Yn plus 1 minus Y1 divided by Xn minus X0. And for the case of minimum liquid to gas ratio, this equation transforms to this form. Ls minimum upon Gs, that is equal to Yn plus 1 minus Y1 divided by, now instead of Xn, you have Xn max minus X0. Now this line, it passes through 2 points. One is X0 Y1 and the other one is Xn max Yn plus 1. And when the equilibrium curve is a straight line, then Xn max Yn plus 1, this point which is lying on the operating line, it also lies on the equilibrium curve. So when you have, let me just show you. So when you have a straight equilibrium curve like this, then the operating line for minimum liquid to gas ratio, so this is Y1, this is X0, and the operating line will be touching the equilibrium curve at this point, and coordinates of this point will be Xn max, and the other y coordinate, it will be Yn plus 1. So that means this point whose coordinates are xn max and yn plus 1. It lies on the equilibrium curve. So therefore, it should satisfy the equation of the equilibrium curve. So the equation of the equilibrium curve, it is y is equal to 0.125x. It is given to us. Now this point should satisfy the equation of the equilibrium curve. So therefore, yn plus 1 will be equal to 0.125 xn max. Yn plus 1 is known to us. You can get xn max. Yn plus 1 is 0.02041. So therefore, 0.02041 is equal to 0.125 xn max. That is 0.02041 divided by 0.125. That is xn max. Therefore, xn max comes out to be 0.163. So in this way, we get xn max. So I hope the steps are clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now after that, let us get LS minimum. And for that, we are going to use the condition for minimum liquid to gas ratio. LS minimum upon GS is equal to yn plus 1 minus y1 divided by xn max minus x0. Yn plus 1 is 0.02041. y1 is 0.00102. x0 is 0.00503. And we have just got xn max. It is 0.0163. So let us use these values. GS is also known to us. It is 0.01054 kilomole per second. The only unknown is LS minimum. So LS minimum divided by GS will be equal to yn plus 1 minus y1 divided by xn max minus x0. Now let us use the values. So LS minimum by 0.01054, that is equal to 0.02041 minus 0.00102 divided by 0.163 minus 0.00503. So I have used the given values or known values. So therefore, LS minimum divided by 0.01054, it will be equal to 0.01939. This difference is 0.01939 and this difference is 0.16. So that gives us LS minimum upon 0.01054. And this ratio comes out to be 0.123. So LS minimum is 0.123 into 0.01054. That gives us LS minimum as 0.00129 kilomole per second. So in this way, we get LS minimum. LS minimum comes out to be 0.00129. So I hope the steps are clear to you. If you have any doubts, you please mention them in the comment section. Let us move ahead. Okay, now let us get LS. LS is 1.5 times of LS minimum. LS minimum we got, it is 0.00129 kilomole per second. So therefore, LS will be equal to 1.5 into 0.00129. That gives us LS as 0.00194 kilomole per second. Now after that, let us get the absorption factor. Absorption factor is LS upon m into GS, that is ratio of the slope of the operating line to the slope of the equilibrium curve. GS is 0.01054 kilomole per second. M is 0.125. We know that. So therefore, A will be equal to 0.00194 divided by 0.125 into 0.01054. So that gives us A as 1.47. So in this way, we get A. Now let us get finally the number of ideal stages by using Kremser equation. The Kremser equation that we have to use is n is equal to, capital N is equal to log of yn plus 1 minus m into x0 divided by y1 minus m into x0 into 1 minus 1 upon a plus 1 upon a divided by log of a. So yn plus 1 is 0.02041, m is 0.125, x0 is 0.00503, y1 is 0.00102. These are known to us. And we just calculated E, that is 1.47. So therefore, n will be equal to log of 0.02041 minus 0.125 into 0.00503 divided by 0.00102 minus 0.125 into 0.00503 into 1 minus 1 upon 1.47 plus 1 upon 1.47 divided by log of 1.47. That is n is equal to log of this product is, first I will take the product. So this is log of 0.02041 minus 0.000629 divided by 0.00102 minus 0.000629 into 1 minus 0.68. 1 upon 1.47 is 0.68 plus 0.68, and log of 1.47 is 0.167. So let us continue with this. So we are getting n. So n is log of 0.02041 minus 0.000629 divided by 0.00102 minus 0.000629 into 1 minus 0.68 plus 0.68 divided by 0.167. So that is n is equal to log of, this is 0.0198 and this is 0.000391 into this difference is 0.32 plus 0.68 divided by 0.167. So that gives us n as log of, this ratio is 8.99, and this is this entire term is 8.99 plus 0.68 divided by 0.167. So that is n is equal to log of 9.67 divided by 0.167. That gives us n as 0.985 divided by 0.167, and finally you get n as 5.98. So in this case, the number of stages required according to Kremser equation, when the equilibrium relationship is given to us, when the equilibrium curve is a straight line, n, we have used the Kremser equation to get the number of ideal stages. So in this case, the number of ideal stages, they come out to be 5.98. So in this way, we end our calculations for this numerical example. We have found out the number of ideal stages by using Kremser equation. So with this, I will end my discussion for this video lecture. I hope you have understood each and every step. If you have any doubts, you can mention them in the comment section. So thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. From my next video lecture, I will be starting my discussion on absorption in packed bed. So hope to see you soon in my next video. For now, thank you. Have a nice day. Bye bye.